Hi, I am Coach Matt, and welcome to my COVID sanctuary. Today I'm going to be talking about JavaScript closures in depth. If you've written any amount of JavaScript before, you've used closures. You may have not known it, but I want to help you understand what a closure is, how it can be used, show you a few practical, useful use cases for closures. One of which is higher order functions. So we're going to be starting with a slow implementation of the Fibonacci function. You may have seen this one before. This is actually exponential runtime. We'll demonstrate why soon. But imagine a higher order function that can wrap that Fibonacci function, give you a new function back, and then now that function is actually order in runtime. So we can do this. We can actually write a generic memoization function to do this by leveraging closures. I'll also introduce a interview question that I've been asked multiple times in my career that goes over closures as well. Let's jump into it. Okay, let's start with MDN's definition of what a closure is. A closure is the combination of a function bundled together with references to its surrounding state. In other words, a closure gives you access to an outer function's scope from an inner function. So there's a few potentially new terms here. There's lexical environment and there's scope. So what do these mean? Let's unpack that, starting with lexical environment. In this function, we've defined two variables, a and b. These variables live inside of foo. They are not accessible outside of foo. So a is not defined. That's going to throw an error. But this works. Now, a lexical environment is a mapping of variable names to variable values in a execution context. And for now, we can think of an execution context as a function. We have variables a and b defined here, and a and b are not accessible outside of this foo function. So a and b are in scope here, but they are out of scope here. They're not available here. Similarly, if we define a and b out here to different values, a is 0, let b equals 5, we can log a and b out. And then if we log them out here as well, we'll see the values are unchanged. And that's because there are two lexical environments here. The outer lexical environment here has a and b with values 0 and 5, and foo has a and b with values 1 and 2. So you can modify these values here without changing the values here. And that's why the values are the same here. However, if instead of defining new variables here, we modify them, now a and b equal 1 and 2 here. This is one of the powerful ideas with closures. You have variables that you can use from parent execution contexts or parent functions. Here's another example where we create an execution context with this remember function. By calling remember with the value hello world, we hold on to that value with this val variable and return a function that we can invoke later and return this variable here. So if we do console.log foo, we get back hello world in our console. Okay, so this is really all you need to know when it comes to closures. Now let's take a step back and think of how we can apply closures to something a little more interesting. Here we have an exponential runtime implementation of the Fibonacci series. So if we try and print out values within this series, you'll see that it quickly slows down. So when we get to the 30s, we can see there's a pretty notable delay, and each subsequent step is going to take about twice as long as the previous one. So why is this so slow? What's happening here is there's a lot of redundant work. So that doesn't sound too bad until you realize the following. Let's say we want to calculate the fifth number. First, we need to calculate the fourth. So that's n minus 1. We also need to calculate n minus 2. And we want to calculate the fourth, so we need to calculate we need to calculate the third, n minus 1, and then n minus 2. Now 2 is one of our base cases, so our recursion ends there. But 3, once again, fib n minus 1 and fib of n minus 2. Same thing over here. So you'll notice that there's some redundant work here. So this is the same as this. You can see how this adds up pretty quickly. It would be great if instead of doing all this work twice, we could just remember that fib of 3 equals this value. So what we can do is we can just memoize the results. So fun fact, memoization is a type of caching where there is no invalidation. You can hold on to the value indefinitely. You don't have to, but memoization assumes that given an input, the output will always be the same. So let's say if n is in our cache, return cache of n, cache indexed at n. And then when we compute a result here, let's store it in the cache. So if we save this, we'll see that we calculated the 99th term very quickly. Great. And it looks like we're actually losing some precision here, so let's maybe calculate up to the 70th term. Now that we have a working optimized solution, let's think about this again from the ground up. We'll see that this line of code here and this code here has really nothing to do with the Fibonacci series. So it would be nice if we were able to abstract that functionality away and reimagine our memoization function. So what do we know about our memoize function? Well, it takes a function and returns a function. And with that, we know in our memoize function here, we need to return some function. What else? At some point, we need to call this function that's being passed in. So for now, let's just return that function being called. And we'll remember too that our fib function takes in one argument. So since this is the function here that's being returned, let's use that one argument and pass it back in here. So if we save, we are back to our slow implementation of Fibonacci. However, we can use the parent execution context of this anonymous function here and create a cache for us to use. And using the same logic as before, we can once again optimize our Fibonacci function. So if I save, it's fast. Great. So what's going on here? We overwrite fib with the returned function from Memoize. And this function here has a reference to this cache. So this cache will operate independently of, say, another memoized function. So if we call identity, we'll see that our fib values remain unchanged. Also, we'll see that this original definition of fib also references the fib variable itself. So remembering that this fib is a reference to a function itself that is being overridden here, we realize that when we recurse and call fib, we are actually calling this function here, which is how we can have a recursive function use this cache as it recurses. So we still have our Memoize function hard-coded to only accept one argument. Let's work on making that more generic. If we spread our arguments into this args array, then what we can do is we can construct a unique key based off of our arguments. So now we will just be checking for the existence of this key, and then we will call our callback with the original arguments. Great. And then now we see that our Memoize function can work with multiple arguments. Awesome. You also may notice there are a couple potential issues. So we're assuming that each argument is stringifiable, which isn't always the case. So sometimes some objects do not stringify in a useful way. So this line stringified looks the exact same as hello. So that's a potential issue you need to be mindful of if you use this. And then there's some ways you can create similar keys if your arguments stringify this. So you might need to do some escaping of characters. But other than that, this is a Memoize function that you can apply to any pure function in JavaScript. Okay, so here we are, the famous interview question that I see all the time. So I think we all understand enough about closures now to really see what's going on here. We see that there is this anonymous function that is logging out I, and we see there is a variable I defined in this parent execution context, which this function has access to. And we also know our set timeout, even when given a value of 0, is this callback is going to execute after all of this code runs. So, given that, what do we think is going to be printed out here? You can see down here, after I save, 333. So what happens is we iterate through the loop. When I equals 3, this condition is now falsy. We exit, and then the event loop will begin running these asynchronously, these queued up callbacks. And I is still 3. All right. I put a lot of time and energy into this video and made a quiz that you can take to help some of these concepts sink in. So I highly encourage you to check out the quiz and see how you do. As an engineer, you know that reading and watching versus actually doing something is a very different experience. Thanks for watching. I hope you found that informative. Remember to like, comment, subscribe. Once again, my name is Coach Matt, and I help front-end engineers find the jobs they want. All right. Thanks for watching. Yeah, thanks for watching, and good luck in your next interview. Thanks for watching, and good luck in your next interview.